we're going to go ahead and really try to solve some application problems having to do with exponential functions. So I just happen to write down at the bottom here problems 6 and 8 off of this list right here. And these problems should be similar to 6.3 in your book, the application problems there. Although we're going to continue to see application problems on both exponential and logarithmic functions. So let's see here. So it says that, let me see if we could zoom in here just a little bit and read this a little bit better. Let's see. I guess I'm going to have to just move this down. Okay, that's a little clearer. So it says here, this function d of h equals 6 times e to the negative 0.4 h can be used to determine the milligrams d of a certain drug in a patient's bloodstream h hours after the drug has been given. So h is the number of hours since the drug was administered, and d is the number of milligrams of that drug still in the bloodstream. So how many milligrams to 2 decimal places, here's our question, is present in the bloodstream after 9 hours according to this function. So here's what we're going to do. Let's just go down here where I have some room. And actually, I'm going to go ahead and do this instead so you guys can keep an eye on the problem at the same time that I work it out. So I'll just put a piece of paper here and we can work right here. So let's say number 6. And I'm evaluating this function at 9. So this is 6. And by the way, as we go through problems, you might want to keep an eye on the following thing. Make sure that your units match. Did you notice in the definition of the function, it says h hours? There are some problems in our textbook where it might say that h is in hours, and then they tell me how many minutes down here, and I have to convert the minutes to hours to use the function. So it turns out in this case there's a match, right? That this is in hours and so is our function. So I'm just going to find d of 9 then, and 6, it'll be times e raised to the negative 0.4 times 9. Okay, and that is exactly what I want to model in my calculator. So I'm going to get my calculator out, put that right next door, and let's see if we can get that to go ahead and evaluate that particular result. So we got here, I'm going to go ahead and quit here. I'm going to put in 6, and then if you recall on a previous video or in class, I talked about where to find e to the x. And right down here, it is on the face of the calculator right above ln, so I'm going to hit second ln. And when I do that, I now have the ability to put in that exponent, which is going to be a negative. And by the way, on these calculators, that's for a negative number. This is for subtraction operations, right? So I'm going to hit this. And now I'm going to go ahead and put in the exponent. Oh, I'm getting a little glare there. That will work, I guess. 0.4 times 9. I could put it in the parentheses, but I just hit times. And I should get the answer. Okay, and it looks like the amount of milligrams is I think it told us to round off to the second decimal place, 0.16 milligrams per, does it tell me? No, I'm going to guess it might be something like per liter, but it doesn't tell me. It just says the number of milligrams of a certain drug still in the bloodstream. And so maybe it's not a rate. Maybe it's a total number of milligrams still in the body. But it turns out here that my answer is 0.16, rounded off to the second decimal place, milligrams. And we'll go ahead and take a look here. It looks like the answer is B if you take a look up there on the multiple choice options right here. It looks like it's this answer right here. Okay, let's do a second problem. So I picked number 8. And right here it says the rabbit population in a forest area grows at the rate of 6% monthly. If there are 230 rabbits in July, find how many rabbits, rounded to the nearest whole number, should be expected by the next July. Okay, so now this is an example of actually what I was explaining earlier to make sure that your units match your function definition of units. Did you notice that this growth rate is monthly, 6% per month? So what I'm going to do, did you notice that we went, it says here, should we expect the next July? That's really 12 months of growth in the rabbit population, and this does assume that none of the rabbits that were born died, that we're just seeing the total number of rabbits, right? And so what happens here, we have to use for t, which is defined to be the amount of time. Where does it say that here? I just want to point that out. Maybe it didn't define it here. Okay, I'm going to have to assume it, but it should have defined t to be the number of time, the amount of time that transpired. We're going to go ahead and use 12 for months because it did define it to be monthly, right? And so I'm going to go ahead and evaluate this function using 12 for t because 12 months transpired from 1 July to the next. And so I'm going to really evaluate this function for y is equal to all of this and then 12 for t. And I'm going to get here y is equal to 230, which was our original population, times 2.7 raised to the 0.06 times 12 power. And the rest of it is nothing more than being comfortable on your calculator doing computation with exponentials, right? And so what I have here, and I'm going to try to put this all in at once, now I have to be a little careful. Did you notice this 230 is times 2.7. It's only the 2.7 that is being raised to the power. So I'm going to do 230, and then I'm going to say parentheses, 2.7, close the parentheses, and raise only that parentheses, right? It's going to know that there's multiplication here, and it's only this base, 2.7, that gets the power of, right here, 0.06 times 12. And I hit enter. And it looks like the rabbit population more than doubled, right? It's 470. It said round to the nearest whole number, so this would be 470. And looks like our answer is A, because right up here you can see it says 470 right here. And that answer is A.